Hello everyone. We present our SOC4 Association Transformer for multi-label classification. Institutions including 5 sections. We first give introductions, then we talk about the motivation of our work. Afterwards, we show our approach and evaluate the proposed model with experiments. Finally, we give a conclusion on our study. Image classification is a fundamental task in computer vision. A traditional image classification problem where each image contains a single object. The learning task for given image is to predict the categories of object content in it. However, real-world images often contain multiple objects and is essentially complex, which makes it challenging for the model to understand things. Therefore, multi-label object recognition is an essential task in our natural world. In a study on multi-label classification, there exists 2 problems. First, positive-negative label imbalance. For a typical multi-label setting, averagely, an image has only few positive labels or many negative ones. Therefore, this positive-negative imbalance dominates the optimization process, resulting in poor accuracy. Secondly, the tiny object detection. Even those convolutional neural networks shows impressive success in computer vision, as well as in multi-label classification. Our critical issues in the conventional CNN model is the difficulty in tiny object detection. Due to the attributes of the convolutional and the polling operation of CNN, the low pixels of tiny object on the image is easily ignored during the feature extraction of the CNN-based backbone. On the label imbalance issue, people propose to loss functions asymmetric loss to overcome it. ASL adopts asymmetric focusing and asymmetric probability shifting to dynamically operate on negative and positive samples. Compared to previous loss function of multi-label classification, such as cross-entropy and multi-label software margin loss, ASL shows tremendous improvement on performance and becomes the current stands loss function in multi-label classification task. In our work, we adopt ASL as a loss function as well. Our study concentrates on the tiny object detection. Since the drawbacks of CNN, we propose to adopt Vision Transformer VLT as a feature extractor. VLT, built up with self-attention module, shows tremendous potential in different computer vision downstream tasks. Due to the attention mechanism design, VLT captures the global information and is an efficient feature extractor. Considering the co-occurrence of different objects in the same image, label association is widely used in multi-label classification. For example, a bag is more likely to be associated with a person than a dog. The previous works proves that label association can boost model performance. Therefore, we propose to combine transformer and label association together in our work. The figure illustrates the overall architecture of our model. We leverage the transformer as a backbone feature extractor and get the extracted feature L. We forward L through a association module to calculate the association map A and output N1. Meanwhile, we got another output N2 by forwarding L through a fully connected layer. The final prediction is the future operation of the N1 and N2. In our work, we adopted 2 variants of VLT as the backbone, Schwann transformer and CVT. For simplification, we summarize the transformer places, which are treated as the standard operation. We can describe the operation of VLT in 3 stages. The first stage is patch embedding. We divide the 2D image into several patches and use the patch embedding to convert the 2D input into 1D embedding. Afterward, we apply the multi-pad self-attention MSA to process the embedding. Finally, we forward this feature through a multi-label perception MLP for output. The previous works mainly adopted the graph convolution operation to process the label association. It needs the niche graph and is unfriendly for computation cost. Therefore, we propose a association module, a simple but efficient method. The input feature of AM is extracted feature L from the VIT. The processing of AM is following. We first unsqueeze the feature L and conduct a 1D convolution to project a 1D embedding to 2D features K and N. Then we transpose the feature K and conduct a multiplication with the K itself, attached a sigmoid function to calculate the association map A. We finally multiply feature M with the association map A and apply another convolution of 1D to get output M1. It should be noted that there is a stark difference between self-attention module and our model. The purpose of the association module is dynamically learning and aggregating the interclass correlations through model training. Therefore, association module works on a class domain. Meanwhile, self-attention works on a special domain of the input image. We have mentioned that we adopt ASL as a loss function in our implementation. Due to the long-tail distribution of the object correlation, we found out that association map A is easily overfitted. Therefore, we use the L2 regularization on the association map with a non-negative parameter theta. We evaluate our model by two public benchmark datasets, MS-COCO and Pascal VOC. The MS-COCO dataset has 2,801 training images and 40,504 validation images. It has 8 classes with average number of 2.9 object labels per image. The Pascal VOC dataset has 5,011 training images and 4,952 validation images. It has 20 classes with average number of 2.5 object labels per image. The performance metric is the mean average precision, MAP. The quantitative results of MS-COCO are reported in Table 1. We compare our model with 10 baseline models. The proposed model shows superior performance. To further validate the significance of adopting the AM in our model, we performed the ablation study as follows. We remove the AM from our model and only leverage the transform backbone to obtain the two models as baselines, namely Schwann L and CVT 24W, respectively. Experimental results show that the performance of both Schwann L and CVT 24W are significantly improved by integrating the AM, which confirms the effectiveness and the significance of adopting AM in our model. The quantitative results of Pascal VOC are reported in Table 2. Our proposed model shows superior performance in terms of each category accuracy. Both our models outperform other baseline in the training objects, such as Boto and PET. The result is jointly contributed by the transform-based backbone and the association module. Finally, we visualize the association maps of different regularization. We visually show that the object AM in the cases of adopting different regularizations, namely L1 regularization, L2 regularization, elastic net regularization, and nuclear norm regularization. From the image, it is observed that AM maps memorize most object association without any regularization term. The Table 3 shows the L2 regularization outperformed others in terms of the model performance. In our studies, we proposed a subformer which contributes a transformer backbone with a lightweight association module. For the task of multi-level image classification, we evaluate our model with two public benchmark datasets. The results show the proposed model metrics outperforms real works. We found that the form of regularization on the association matrix is critical for solving overfitting the association map. That's all. Thank you for your attention.